Hi, my name is Zhang,
And I'm Sophia Jin.
and this is our investigation of chitin-enhanced seaweed scaffolds for cartilage regeneration. So, osteoarthritis is a degenerative joint disease that affected 7.6% of the world population in 2020 and is projected to rise by 60 to 100% by 2050, as seen in Figure 1. OA patients pay tens of thousands of dollars for treatment, not including surgeries, in Figure 2, which can amount to hundreds of thousands of dollars that are only temporary and has to be replaced every 10 years. On the other hand, seaweed scaffolds are much cheaper to produce and provide more long-term effects.
Osteoarthritis patients experience joint pain and stiffness. So as you can see in figure 3, this is caused by swelling in the synovial membrane and cartilage thinning. So one way to remedy this is by implanting scaffolds directly into the joint to accelerate the growth of cartilage cells. Seaweed is a great biomaterial for this purpose because of its high cellulose content. And as you can see in figure 4, cellulose is high in hydroxyl groups, and this is what allows it to retain a rigid and hydrophilic structure in vivo. The rigidity of seaweed scaffolds gives it some advantages over conventional hydrogels, which have some limitations in terms of long-term stability. And in addition, invasive seaweeds like ulva and sargassum, which were the ones used in this study, can be obtained at a very low cost from coastal blooms.
In terms of the literature review, Barshai et al. Found ova to be an effective biomaterial because of controlled proliferation and non-toxicity. On the other hand, Barry-Kilgore et al. Found ova to be inefficient, and out of these three, only E. radiata was able to achieve non-toxicity and proficient cell adhesion and proliferation. Because of this discrepancy with the ova scaffolds, we decided to investigate the usage of the ova, and in place of the E. radiata, we chose a different species of brown algae called sargassum, and because of the environmental implications through the Great Atlantic Sargassum Belt.
The purpose of this study was to compare D-cell ulva and sargassum enhanced with chitin as biomaterials for cartilage scaffolds. We wanted to do this using a cost-effective and environmentally friendly approach, and we hypothesized that there would be a significant difference in protein sorption, degradation, hydration, morphology, and molecular composition between ulva and sargassum scaffolds with and without chitin.
In phase 1, we decellularized the scaffolds by first soaking them in sodium dolichosulfate and then soaking them in TX100 and bleach before rinsing them with deionized water to remove any excess chemicals. We also made a chitin sol gel, which was applied using the setup in figure 19. As you can see in figure 10, the decelled scaffolds had much less pigment compared to the native seaweed, which we compared using the mean grade value in image J. But the main thing we noticed was that the ulva scaffolds decellularize at a much faster rate compared to the sargassum, likely because of its weaker chemical structure, since it's mostly composed of ulvan polysaccharides, which are high in sulfate groups and can cause electrostatic repulsions. Sargassum, on the other hand, is mainly composed of alginates and fugitins, which support a stronger backbone.
In phase 2, we tested protein sorption using a BCA protein assay. So we did this by incubating the scaffolds in the protein BSA, then adding BCA for detection and measuring absorbance at 562 nanometers. Then we estimated the adsorption using a standard curve. So as you can see in the graph, there was no significant difference between any of the groups compared to the control, which suggests that there's insufficient protein binding. But it's also important to keep in mind here that the BCA reduction reaction depends on a basic environment. And at this pH, serum proteins like BSA have a net negative charge. So there could have been some electrostatic repulsions between the BSA and the carboxyl and sulfate groups in the scaffolds because those are also negatively charged. However, the pH of the human body is closer to neutral, and in the joint it's actually more acidic. So the negative charge of the serum proteins is less pronounced, which means that results might be different in vivo. This shows the limitations of using only acellular assays to predict cell behavior, as we were unable to do in vitro cell seeding due to storage restrictions. In the next phase, we tested degradation by measuring or weighing the scaffolds over 30 days, and based on the degradation curves, ulva degraded rapidly and erratically, which was likely because of its amorphous structure. And as you can see, the sargassum curve is more similar to the literature curve, which we derive from the growth rate of cartilage. And of course, in vivo, cartilage does not grow at a steady linear rate, but this is just an approximation. And it's important to make sure that the two align, because the ultimate goal of the scaffold is to degrade as the tissue grows and be replaced so the tissue can become self-sufficient. In both cases, you can see that chitin increased stability, which was likely because its beta-linked backbone added support. In phase 4, hydration was measured using a gravimetric swelling ratio assay, and we found that sargassum scaffolds had a significantly higher swelling ratio than ulva scaffolds. And past studies have also found that swelling ratios less than 4 are inadequate for nutrient diffusion, while those greater than 10 are considered optimal. So these lines are also indicated on the graph. And as you can see, sargassum scaffolds fell into the optimal range, while ulva was in the inadequate range. And this is significant because it shows that ulva scaffolds would not be able to sustain proper cell growth in vivo. For both types, chitin significantly reduced hydration, but this was somewhat expected because of its hydrophobic structure.
We also analyzed the surface morphology of the scaffolds using scanning electron microscopy, which was conducted at the NYU Grossman School of Medicine Microscopy Corps. As you can see in figure A, the sargassum exhibits more of a fibrous structure, while, as you can see in figure C, the ulva exhibits more of a mesh-like smoother structure. So this likely indicates that the sargassum has a higher surface area, whereas the ulva has a lower surface area, which would mean that the sargassum would allow for better cell adhesion and nutrient diffusion as well. In both cases, the addition of chitin covered a lot of the underlying area, creating more of a homogeneous texture, which would significantly reduce nutrient diffusion, also explaining why hydration decreased with the addition of chitin. We also analyzed the chemical composition of both scaffolds by conducting FDIR at microvision laboratories. There was a presence of cellulose in the sargassum scaffolds, but this peak was significantly lacking in the ulva scaffolds, mainly because we were unsure of the methodology used to conduct the test. But in both cases, there was a presence of sulfate and carboxyl groups that support the presence of polysaccharides like olivin in ulva and alginates and fucoids in sargassum that are essential for supporting cell growth.
In conclusion, the results rejected the null in all assays except for BCA. So sargassum scaffolds were more compatible with cartilage growth rate, and they had a higher surface area for water retention compared to ulva, which would make it more effective for aiding in cell proliferation in vivo. They also fulfilled the cost-effective component of the engineering goal, because each scaffold only costs around $2, which is much more affordable than traditional surgeries and more accessible to areas with less complex technology. Overall, these findings support non-chitin sargassum scaffolds as a sustainable biomaterial for cartilage regeneration. And future studies should aim to use in vitro cell seeding to get a better look at actual cell matrix interactions, and then consider using atomic force microscopy to characterize the mechanical strength of the scaffolds, because it's also important to make sure that that aligns with the mechanical load of cartilage in vivo. And chitosan, which is a less hydrophobic form of chitin, could be explored as a way to improve durability without compromising hydration, as we saw with the chitin.
These are references, and thank you for listening.